the Hadley cell that you were introduced to earlier gets broken down into 3 cells. And those 3 cells give us our global winds. They have names. In the northern hemisphere, we have the polar easterlies, the westerlies, and the northeast trade winds. In the southern hemisphere, we have a mirror image. We have the southeast trade winds, we have the westerlies, and we have the polar easterlies. Let's look at this is what the actual circulation looks like because our Earth rotates. We have these thermal highs and thermal lows, and that's what sets the stage for all of this. Remember, Mother Nature abhors the fact that there is more warmth, more solar insolation in the tropical regions than there is in the polar regions. So trying to balance out the imbalances in heat on Earth. That's what these wind systems are all about. So we have the thermal high pressure system in the polar regions, and we have the thermal low pressure system in the tropical regions. And we call that the equatorial low. So it starts out just like with a Hadley cell. The air begins to move from the polar regions as it sinks, and in the equatorial regions, because the air is warm, it's going to rise. So see that red arrow right there? That's the rising air. Here in the polar regions, this is the sinking air. So it's headed down our way from the polar regions. This air is headed up toward the North Pole from the equatorial regions. All right, but what happens? Well, let's start up here with the polar easterlies first. That air begins to move, and remember Coriolis is maximum in the polar regions, so we have that maximum deflection. So if you are stickman up here and you're viewing that air, then that straight line motion is deflected to your right. So winds are named for the direction that they blow from. So because these are coming from the east, here's west, these are called the polar easterlies. Okay? Now, let's head down here to the equator. This air begins to rise, and it moves to the laser pointer, and it moves to the north, where as it rises in the atmosphere, guess what happens to the temperature? It begins to cool off. So it starts sinking and heading back toward the equator. And when it does, Coriolis deflects it to the right. Winds are named for the direction that they come from. So these are coming from the northeast. These are the northeast trade winds. Down here, same thing happens. That air begins to rise, a portion of it sinks and begins to head back toward the equator, and it's deflected what direction in the southern hemisphere? To your left. So these are coming from the southeast. Those are called the southeast trade winds. The trade winds of history. This is how ships used to move from one place to the other. The only thing that could move them was wind. So if they wanted to come, if you're over here in Great Britain and you want to come to the New World, then you have to get into the northeast trade winds to do that. Now, what about these winds right here, the westerlies? Only a portion of that wind, or sorry, that air started sinking. The rest of it headed off toward the North Pole. So what happens? It's deflected to the right because it's moving from here. So if we put Stickman here, and Stickman is watching that air move, he would see it's deflected to his right. So those are now the westerlies. This is the west. The wind is moving from the west. So the westerlies. We've got a mirror image in the southern hemisphere. Westerlies and polar easterlies down here that aren't being shown, but they're there. All of the storm systems that we get, these mid-latitude cyclones that we'll talk about in the next chapter, they are steered by the westerlies. Okay? Now, if we're talking about this air movement, remember we had two types of pressure systems. Thermal highs and lows that are produced just from differences in temperature, and dynamic highs and lows that are produced by movement of the air. So in a low pressure system, dynamic low in the northern hemisphere, it's counterclockwise into the low. Well, look what happens when you put the polar easterlies and the westerlies together. By the way, that's that polar front zone. That's a very stormy region. But you put those two together, that's counterclockwise motion. So the polar easterlies and the westerlies make up a semi-permanent low pressure system. And it would be a continuous low pressure system, but we have a big old landmass that breaks up the air. So we have one semi-permanent in the west, and we have one semi-permanent low pressure system in the east, and they have names, and we'll get into those later. All right, what about the the westerlies and the northeast trades? Well, this is very easy to see, right? Look at that motion. Clockwise. Here's the higher pressure. Why is that higher pressure? Look at what that air is doing. Sinking air produces high pressure. Rising air produces low pressure. Sinking air is stable. Rising air is unstable. So this is a high pressure system here, and it would be continuous if we didn't have a landmass here, but we have these high pressure cells that are one on the west and one on the east side of North America. And we'll talk about the names. Now, what about the southeast trade winds and the northeast trade winds? Look what they're doing. Those winds are converging on each other. And when air converges, the only place it has to go is up. So that is called the equatorial low. The other term for that is the intertropical convergence zone. Intertropical, between the tropics where the wind is converging. So this is the area of always just rainy. The old sailors called this the doldrums because it was the same old monotonous weather all the time. Hot, muggy, storms in the afternoon, next day it starts all over again. So the doldrums. And we got a lot of names for this. The doldrums, the equatorial low, but increasingly you'll hear this referred to as the intertropical convergence zone. And this is important. We'll see why a little bit later. These are our wind belts, and these are the pressure belts as a result of these, of the air motion. Here's our high pressure system on the west side of North America. Here's our high pressure system on the east side of North America. And look at the circulation, clockwise out of the high. These are our low pressure systems here, counterclockwise out of the low. Mirror image in the southern hemisphere. Here's our ITCZ, where we have the northeast trades and the southeast trades converging upon each other. So back in the day, before there was steam, ships would come to America when they would get into these northeast trade winds, and then to get back home, they would be pushed back home by the westerlies. Let's see that again. They get into the Northeast trades to be pushed to there's two Americas, no pun intended, North America and South America. So they would be pushed to America, and then they would be pushed back home. These are our global high and low semi-permanent pressure systems. Semi-permanent because they move with the sun. Intertropical convergence zone, formed by the convergence of the northeast trade winds and the southeast trade winds. Plenty of available moisture, heat builds up, clouds build. This area is characterized by clouds and rain. The winds are calm or light. Doldrums named this area because of the monotonous weather. Subtropical highs form between 20 and 35 degrees latitude, north and south, characterized by sinking, stable air, stable air, cloudless skies. Sailors called this area the horse latitudes because that sinking air sometimes meant that the ship couldn't move and they might be stuck in these areas for a time. Now, legend says, and even the history books say, that because the horses that were being carried on the ships were competition for food and water with the sailors, that they shoved the horses overboard. I just never did understand that, because if you're hungry enough, you'll eat a horse. So I don't know why they got rid of a potential food source, but apparently they did. And these are formed by the circulation of the westerlies and the northeast trades. So clockwise motion. Now, the one that impacts the eastern side of North America is the Bermuda High. The one that impacts us here in the western part of North America is the Pacific High. It's called the Bermuda High because it's generally placed over Bermuda. In the winter time, the high pressure system moves back toward Africa, and it's called the Azores High. Now, one of the attributes of subtropical highs is that sinking air. Deserts, the major deserts of the world, if they're not interior deserts like Mongolia, they are impacted by the fact that air is so stable when there's no rain. So the Mojave, the Sahara. Then the subpolar lows are formed by the convergence of polar easterly winds and the westerly winds. They dominate weather in the winter when the subtropical high goes south with the high sun. Cool, moist air. Western North America, Aleutian low. This storm system that we are experiencing right now, and if you hear this maybe in another semester, we might not be experiencing a storm system, but the air is really, really cold. It had been fairly warm over the past few days, but now it's kind of chilly out there, and that's because this air has been cranked down out of the Aleutian low from the North Pacific. Eastern North America is dominated by the Icelandic low in the wintertime. The polar highs, heavy cold air in these polar regions, that's the Antarctic high and the Arctic high. And here they are again. Here are the wind systems. Polar easterlies, westerlies give us the Aleutian low over here, the Icelandic low over here. This gives us the Bermuda high over here and the Pacific high over here. Okay, I have two pressure maps for you. This is the January pressure map. This is summer for people in the southern hemisphere, but it's winter for us. So we now see this Aleutian low, and we see the counterclockwise movement of air into that low. and the Pacific high here in that clockwise motion. Here's the Icelandic low right here, that counterclockwise motion. In the wintertime, so this high pressure system has shifted back toward Africa, and it's the Azores high. And look at this, the side that, what side of the high, I'll get it right here in a second. Look at what side of the high pressure system the Sahara Desert is on. You guessed it, the sinking side. And sinking air is stable air. Look at the sinking side here. We have deserts here. We have the Sonoran Desert, we have the Mojave Desert, we have the Chihuahua Desert in Mexico on the sinking side of the high pressure system. So that brings up a question that I will get into. This is the summer pressure map, and look at what has happened in the northern hemisphere. Do you see that Aleutian low anywhere over here? No, you do not, because what has happened? The Pacific high has moved north with the high sun. All this moves with the sun. These belts move with the sun. The pressure systems move with the sun. So the Pacific high is now dominating our weather in the summertime. The Aleutian low, that's where our unstable air masses break out of so that we can get rain and snow in the wintertime as a result of the orographic uplift when that air moves up over the Sierra Nevada. But summertime, none of that. It's just hot, dry, hot, dry, hot, dry. The Bermuda high now is what we're calling this because it shifted back toward eastern North America, and the climate here in the southeastern part of the U.S. is totally different, even though both of them are dominant than the West, even though I get too excited about this, even though both of them are dominated by high pressure systems. But look at which side of the high pressure system the southeastern part of the U.S. is on. It's on the rising side of the Bermuda high, and that air is coming from over the ocean, so you know it's moisture laden. Rising air is unstable air, so we end up with adiabatic cooling taking place, and we have a lot of rain here in the summertime. Totally different here. We're on the sinking side of this high pressure system, so sinking air is stable air. We're not going to get any massive rainfall amounts in summertime. We're lucky if we get that in the wintertime. The Icelandic low has shifted, so we're just it's just a low pressure system up here. Now I will say this: if these high pressure systems are located over a big old landmass, it doesn't matter which side you're on. You've got to have some moisture. You've got to remember what your recipe for a cloud is. You've got to have water vapor. You have to have condensation nuclei, and you have to have cooling temperatures. So you might have that, but if you don't have the water vapor, you might have condensation nuclei and cooling temperatures as the air rises. But if you don't have water vapor, there's nothing that's going to happen with it. Then the ITCZ, shown by this purple line right here, which I didn't even mention back on the other map, but it has moved with the high sun too. If you go back to that winter map, you'll see that it is down here. It's to the south, but it shifts with the high sun as well. And there are places in the world that no matter if it does shift to the north or south, there are places that are always under its influence. And that's where we have tropical rainforests, like the Amazon, the Congo here in Africa, Indonesia, portions of Southeast Asia. It's that unstable weather associated with the intertropical convergence zone. All right, now I'm sure there's some things that I forgot to tell you here. If you all have questions about this, please let me know, and I'll see you the next time.